Hello everyone. In this video we're going to be talking about some of the backend of Olin Electric Motorsports CAN API. As a reminder, this is a library that was written by the team to abstract low-level CAN bus interaction, specifically for the STM32G4 microcontrollers that we use. This video is going to focus more on how this library works, again on the backend side. If you're interested in how to use this library in your own project, check out the other video we've recorded on using this library. Additionally, to understand if you're ever working on this library yourself, I recommend learning a little bit about the CAN protocol itself. It will be helpful, and we've linked a couple video resources in the description covering that as well. Okay, as I mentioned, this library abstracts the low-level peripheral level code for STM32G4. This library is built on the HAL abstraction from STM for the STM32G4. And for a little bit of history about this library, our team has had some form of a CAN API for quite some time. Most recently, we had this version of the library was developed really for the Atmega 16M1 microcontrollers. And then recently, in 2026, we refactored, migrated this library to function with our new STM32G4. And a quick note here is we call it the CAN API. We might call it a CAN library. It's worth mentioning that we called it CAN API, but this is very much a local API. It's not like when you hear the word API, you might be thinking, oh, I'm sending some sort of web request. But no, this is all local. You can think of it maybe as a library, as an API, whatever makes sense to you. But yeah. The purpose of this library, why does it exist? It reduces repetitive code. A lot of that low-level code is the same across projects. So we kind of bring it out to one place to reduce errors, make it easier to write your own code, allow you to spend more time doing interesting stuff with your project as opposed to chasing down interesting CAN errors. This project allows you to write all your CAN messaging, receive and publishing in YAML, which is a very human-friendly language. And it also unifies all our project across the repository into one, allows us to unify that into one cohesive DBC file, which is a CAN database. And that's useful for our team because it allows us to use other tools such as our CAN viewer with that DBC file. Okay, that's a brief overview. Let's start to dive into how it works. Moving on over to this whiteboard. This is kind of a high-level description of the flow of our library. I'm going to start off over on this left side. This is kind of the individual project level kind of implementation code. Hopefully, if you've been with us on the team, this general structure looks familiar. You have a YAML file, a header file, a C file. This is for the BSPD, but we can replace kind of that file path with wherever your project would be. But taking a brief look at this YAML file, this, as we covered more in depth in the usage video, is where we define the messages and signals that we're publishing, as well as the messages we are subscribing to. And again, these YAML files are how our library works, our CAN API works. So let's take a look on what that looks like. So using the information from this YAML file, we can go over to this rightmost column, which describes our actual CAN API library. And there's kind of two main functions of this CAN API. On one end, we have our DBC generator. This generates that CAN database file. Again, from those YAML files, as well as the C generator. This generates like source C code that we can use in our actual project to actually do the sending and receiving of the messages. From this C generator, we have these two template files we call that contain template code for the C file and the header file of those kind of custom functions, which we'll take a look at what that actually looks like in code in a second. But just know that these are template files that are populated based on whatever content's in the YAML. And then from those template files, we kind of, as we say, we populate them, and then and all of this, the population is done at compile time, which means each time you run Bazel build, this whole process will run once again. So we Bazel build, we fill in essentially these templates with the information from our YAML, and that generates these compile time files, essentially in the same directory as your project. Can API.h, can API.c. Additionally, in sort of the backend, we have these can tools files that are also generated at compile time based on the DBC, generated by Bazel. And these are generated using the can tools Python library. That's an external library, not something we've built at OEM, that we kind of use as a backend to parse through DBCs and kind of encode and decode CAN messages into source C code. So we don't have to worry too much about this, but moving back up to here, these are the ones that are more relevant for our own projects. And this can API.h is actually what's included in your main, again, project level implementation code. We include that can API.h. And that gives us access to all these functions, such as the can init, the structs, which we've covered in the usage video, and the send functions, receive functions, and such forth. Okay, that's a high-level description of how these things all relate to each other. We're going to switch over now to look at some of the actual code to kind of get a glimpse of how it really works. Okay, here we're moving into the OEM monorepo. All our CAN API library functions are housed within common and the CAN API folder. So a couple things to notice on this folder. We have templates, which we'll look at in a second. We have utils, which just has some Python functions, like supporting helper functions for the Python files. And then we have our two main functions here, the cgenerator.py and the dbcgenerator.py. We're going to start by taking a look at this dbcgenerator.py and try to understand what's going on here. Couple things to notice right off the bat. You can see we are importing from CAN tools, which is again that external Python library that we use. The function of this Python script is to generate the DBC. How we do that is we actually use like essentially a command line, a CLI command, and where we create a command line command that Bazel then will run. So a little confusing to like think about, because normally when we think of command line interface, we think of ourselves running the commands. But in this case, the Python file kind of structures the command, and then Bazel is the one running it. So we're using the argparse Python library to accomplish this. And the kind of first section of the code here is essentially formatting the command, adding arguments, like argument options, and then we actually kind of run the command through Bazel. With the command run, we can now or once that command's run, we can do the thing we actually want to do because we have all the correct arguments. And that is to create the database. So again, we're using this CAN database Python object, which comes from the CAN tools library. And we create an empty one here. We add in any existing DBC files that were passed in to that command line argument. And then we add in YAML files that were passed in. And essentially, the CAN tools kind of handles most of the hard part for us, and we'll create a new DBC for us. Okay, moving on to the kind of C side of things. We're looking at cgenerator.py here. And we're going to do a similar kind of walkthrough of what's going on here. Again, you'll see we continue to use CAN tools to parse our CAN database, DBC. We also use the Jinja 2 library. This is a templating engine for Python. So it allows us to create templates and essentially fill in templates, which is what we use to create our C code. So looking at the main function here, we start with a similar sort of structure as the DBC generator. We create a command line command using the argparse library from Python. We take in a bunch of arguments, and then we use those arguments, which were again supplied by the Bazel command, to do what we want, which in this case is generate the C files. We start with looking at the CAN database. We create a blank database, and we fill it in with the database that was passed in to our as an argument. With this database, we also take a look at the, or aside from the database, we take a look at the YAML files once again, which again are passed in as argument. And then the kind of following code, so that kind of gets like the whole, DBC relates to the whole car that contains information for all the nodes. But the kind of following section of the code relates to the specific node we care about. So if we copy back to here, this example is focusing on that BSPD node. So in this case, the code here would focus on BSPD. That would be the node we care about. And this code is essentially repeated for all the nodes on the car, kind of one by one. And hopefully that'll make sense as we continue to explain what we're doing. So once we know which node we care about, we need to figure out which messages that node transmits and receives. And how we do that is, as you might suspect, is through that YAML file. So this loop here goes through all the messages to publish that are described in the YAML file, the messages and the signals, and it essentially appends it to a couple lists here, as well as likewise for the subscriptions. We kind of parse through that YAML file, and everything we say that we're subscribing to, we add it to one of the lists here. And then why do we want those lists? We want those lists to populate our templates. So this kind of sets up the template structure, again, using Jinja 2. And then this is sort of the interesting part where we actually, what we call render the templates, or fill in the templates with the information that we got from the YAML files. So you'll see TX messages, RX messages, choices are all those lists that we got. from those YAML file for our specific node. So this lets us create, based on the template, an individualized header file and C file for our node. So that was a lot, but hopefully that makes some level of sense. I also recommend looking through this code on your own, trying to make sense of it. Kind of moving on, what do the template files actually look like? How does that kind of work? Within that templates folder we saw earlier, we have two different template files, one for the C file, one for the header file. We'll take a look at the C file first. So you'll notice it looks a little strange at first. This is all done in kind of like a special blend of C and Jinja 2, essentially is the best way to describe it. So you'll see it mostly looks like C code. We have our C comments here, but you'll have some kind of funny things sticking out. For example, right here. So if you see the curly braces, two sets of curly braces, or curly brace and percentage sign, that means you're looking at a Jinja 2 command. In this case, this is a direct replacement. So we're saying in the C code, once we render, replace this curly brace header file with this name. And if we actually look back at our C generator, we'll see that header file is one of the things we pass into that template. And in that case, it's just a string, right? So what templating engine is doing is when this is run, it replaces this header file, this whole section right here, with that string. And yeah, you'll see that kind of repeated throughout. Other thing to point out is there's certain commands we run like through Jinja, such as like a for loop is the most common one we use here. So you'll see the curly brace percentage sign indicates we're starting a for loop. And again, these variables, it looks very Pythonic for message in Rx messages, where Rx messages is something that we passed in. You'll see like right here, Rx messages. So essentially anything between these lines here will be repeated for every message in Rx messages. Also, you'll notice there's a couple other things we can do, such as lower or find the length using this pipe syntax, where you might normally see a dot. The pipe just indicates it's like suppose like a Jinja modifier. It's worth looking at the documentation for details like that. So yeah, the template files are somewhat hard to read, so we won't spend too much time here going through it. We'll peek at the actual rendered file in a second to look at what it does. Yeah. So I guess important things to know about the header files is or the template files. If you were to say want to make changes to our CAN API library, a lot of the work will happen here. For example, if we ever change our chipset, like let's say we move to a different STM32 series, this is where we'd change the HAL include statement to include a different version, I suppose. This is also where we set kind of our default CAN settings through here. Currently, we have this on the classic CAN, but the STM32G4 does support FD-CAN, and if someone were to take it upon themselves to upgrade our CAN API to support FD-CAN, there would be changes they'd have to make here, including this line and likely some of these other ones. Yeah, so keep that in mind. Like this is, for example, when I was working to refactor our CAN API from that mega to the STM32. Most of my work was done in these template files. And the header file is about the same, what you'd expect to match the C file. Yeah, but as I mentioned, these are kind of hard to read, so it's also worth taking a peek at what the actual rendered file looks like. And if you recall, these files were created at compile time, so they are kind of hard to find. It's not always clear where compiled files go, and there's actually a couple spots you can look for them. I typically go for, well, I guess to find them at all, it is required for you to run a Bazel build command on your node. So for example, in the previous video, we worked on this CAN demonstration node. So for example, for test_rx, we would need to make sure we've run the Bazel build command, which we already have, to get those compile time files. And that you'll know that has run successfully, well, if you don't get any errors here, and you can see these kind of grayed out files in your IDE that like Bazel out and whatnot. Those are the generated compile files. And there's a lot here, and we won't go too far into it, but the short story is if you go to Bazel bin and then navigate to your, we'll go to that same CAN demonstration node, you'll see there's now more files or different files than the CAN demonstration here. So you'll see like for test_rx, there's now, you don't see test_rx under test_rx.c, but you do see some new files. Yeah, this is where the actual .elf file ends up. That's the actual like machine code that ends up on our chip that we flash over to our chip. But in terms of what's relevant to our CAN API, you'll notice that there's 4 files here that were generated at compile time that match this center column here. The first 2 of which are CAN API.c and CAN API.h, and these are the rendered templates. So see, they now just look like C code. And this is where we define the structs, the functions that are used in our code. So again, using our example of the test_rx node, this one's pretty simple. So let's take a peek at, remind ourselves of the YAML. In the YAML, we're receiving this message 1. And then after going through the CAN API, you'll see that in the header file, we now have created a struct called message1. And you'll also notice that in your C code here, we include this can_API.h, which can be confusing at first if you don't see this file in your folder here. That's this file. At compile time, it will be there. So that's how we pull in that like message1 struct, which we then subsequently access in our code. Again, we go into this usage further in another video, so I won't talk too far about that. but that's kind of how it all connects back. So defines the functions and the structs that we use in the header file. And of course, the C file contains the implementation for all of that. Brief note on cantools.c and cantools.h. These are like kind of evil files that have like thousands of lines of code. Again, these are generated by that external CanTools library, so I don't fully understand exactly. I can't describe very accurately to you why they look exactly why they look, but the important part here is that essentially, to my understanding, these contain macros and kind of C code. These encode everything from our DBC into like a C code representation, more or less. And that is used within, we use that within our CAN tools, or our CAN API header and C file. So for example, like this type right here, the message one type, that was generated from, I believe it should be in here. Yeah, it was generated in here, along with every other signal. And to wrap up the kind of how it works section, we'll take a brief look at what's in the kind of utils folder that we glossed over earlier. We have two Python functions in here, helper functions, parse DBC, which is a pretty simple Python function that essentially just kind of a glorified for loop here that lets us get messages from the DBC, in addition to the YAML handler, which is how we actually like kind of parse through that YAML file and turn it into easy to use Python objects within our actual implementation here. So you'll see in cgenerator.py we include that parse DBC, and I think in DBC generator we include that YAML parser. Last points to sort of note about kind of maintenance. Maintenance of this library, updating in the future. I mentioned earlier how hopefully you've seen kind of where the different aspects of this library live. Even if you don't understand it all on this first watch, hopefully you know where to look if you're having issues or need to make a change. A couple things to note maybe would be this is the current versions of the kind of external libraries that the library the CAN API depends on. That includes Jinja 2 at 3.1.2, PyYAML at 6.0.2, and CanTools 39.4.5. If we upgrade these external libraries, we, I guess, need to make sure that our code is updated to reflect that if necessary. So yeah, I think that's all I have to say about maintenance. And I will pass it off to another Jacob to discuss how the CAN API integrates with our Bazel system.
All right, hi guys. So I'm going over how Bazel interacts with our CAN API. So let's go ahead and get started. So as Jacob was talking about, we can go into common, or not here yet. Sorry guys. Let's go to vehicle, examples, and then using the CAN examples. Here is the C scripts that we went over. So for context, Bazel is like our build system for our repo. It basically makes sure all the files are connected and knows when to execute certain scripts that we have throughout the repo. So one of the scripts that it might run is our CAN API, which serves as two different functions, right? It has a DBC generator, and it also runs as a C generator. So I want to just go briefly into the Bazel side of things. So we have this build file here. We have 3 main functions. Again, Bazel cannot see any files unless you say, hey, this file exists. So I'm going to skip over this one for now. We have STM32 firmware. For those who don't know, this is how it links our C scripts to all the libraries that STM32 has on their GitHub. And also some of our other libraries that we use at Olin. We have an export files. This gets used later for the CAN example. Down here, it's just basically saying, hey, Bazel, this file exists. Now I'll go into the CAN API files. So you'll see up here I have 2 load functions, one for the STM32 firmware, and then one for the CAN API files. So if you look here, it goes common, CAN API, and then goes into CAN dev.bazel. So let's follow that. Common, CAN API, CAN dev.bazel. So this is where I created some definitions for Bazel to use. We have 2 main ones. We have the DBC generator, which I'll go into in a second. And we also have the main function in here, I would say, is the CAN API files. This is the file, or this function basically creates, it first looks through your YAML. It says, hey, what are your CAN addresses? What are the signals you're sending? It then takes the information that it needs from the YAML, the DBC, the name from it, and throws it into a template that Jacob talked about earlier. And then it basically, after all that, it takes the CAN tools and then the CAN API, and we'll throw it into, I guess I should go into this as well. Bazel creates a sandbox for all the files to exist in, and that's where Bazel can find everything. It's called Bazel bin, and that's like its sandbox world. So the last command takes the CAN tools and the CAN API files, and we'll throw it into, this last function throws them together into one folder so that we can easily find, so Bazel can find it and link it back to your scripts, so that way the C scripts can be dependent on each other. Okay, so now I'm going to go back to CAN example. So let's go through some of the things that we need to pay attention to. Again, the name of the file, or the C script, and then having the CAN API at the end of it, just so that way you can format it, or that way Bazel knows what to call it later. The YAML script, just saying, hey, this YAML script's here. The main DBC file, which is pretty important. So we'll go ahead and go to that. And then also dependencies like calling on this third-party STM32 cube. So if we go into, so we're in examples right now. If we go into the main build file here, you'll see that we have the DBC gen. Jacob already went over most of this, but I just want to go over how does this DBC gen work Bazel side. So again, we can see that we have this load function up here, and it goes back to CAN defs. We saw that just a few seconds ago. So what this does is it basically runs this every time that it detects. So Bazel, one of the nice things about Bazel is it sees whenever you change a file. And so whenever you run a Bazel build or Bazel run, it sees the differences in any files that you've made, and then will only run those specific files. So it sees that any file that's affected by DBC gen has changed. Whenever you run a Bazel run or Bazel build again, it will fix that and rerun this entire function again. All outputs from Bazel can be found in Bazel bin. So if we go into Bazel bin, and again, Bazel bin doesn't exist until you run Bazel build, like this command right here. Or just any Bazel command, period, inside of our firmware section of the code, because without it, the sandbox never gets created, and Bazel doesn't have any resources. So we'll go into vehicle, we'll go into examples, because I'm just working in examples, not Mark 8 right now, and you'll see, boom, here's the main example DBC file. And then if you look inside our can examples file, you'll see that there's a lot of run files. A lot of this comes from like the other parts of Bazel. But you can see here we have the can API _C, which is the template Jacob set up for running into like trying to set up can for STM32 specifically. And then also can tools, which is our specific functions that we use for can on our car, and the header files for those as well. And these are the outputs that the Python scripts make with the templates found in CAN API. Okay, let me go over CAN API files in just a little bit more detail. So if we come down here, the first thing that we do is we generate C files using CAN tools. So CAN tools is a Python package that we use. If you're interested in the specifics of the functions, you're more than welcome to look it up at CAN tools. But Bazel specifically, we link it in this build file. So we have these tools, and it's calling on it's making sure that Bazel has access to the dependency which is CAN tools. So we'll go down to the build file, and you can see that we have some different functions in here. The primary one that I'm going to go over right now is the Python script, or Python console script binary, which is a function that I take directly from rules Python, which is a Bazel library that we use. So if we come down here, we call it CAN tools client. Let's make sure that we have CAN tools accessible to Bazel. And whenever you run Bazel build, it will make sure that you have CAN tools. Even if you don't have it on your computer, it will find it. Okay, going back to CAN defs. This is where it runs generating the C files with our CAN tools. And then this is the OEM wrapper for our C scripts or C code that our STM32s use. So this runs our C generator, the Python script. And this is how it connects directly to those template files that Jacob was talking about and finding exactly where to go with them. Down here is where it takes our CAN API tools and CAN API file C scripts and doesn't combine them, but puts them in the same folder so Bazel can find them later. Let me go ahead and show you where you can find those if you're interested. So you can go into Bazel bin, vehicle, examples, and then for this specific board that we're looking at right now, which is the can _examples-C, we have can examples. So here is all these different files. Some of these files come from the compiler, which Bazel throws in here. Some are other types of files. But the main ones that we primarily want to look at are the can _API.c file and the .h file for both the tools and API file. So here is the template file that Jacob Keller made. Sorry, wrong one. Oh yes, this is right. Okay. So yeah, here is the template file so that our STM32 has the correct configurations. Thank you so much for watching this video. Hope this helps for anyone who's trying to learn more about Bazel or how our CAN API works.